Well, if you guys have actually reached this last lecture, and particularly if you've done it in the 5 days as suggested, then you deserve a summary because you're probably a little bit overwhelmed by all the stuff that I've been talking about. If you are an investor in the training course and hope to invest in subsequent development programs, then you deserve an executive summary, and you can take this last lecture as indeed an exhaustive executive summary. What I'll do is I'll go through each lecture with one slide per lecture and try and summarize everything. Now, the first two lectures covered the fundamental physics of EmDrive, and the first one was explaining how the technology complies with the conservation of momentum. This is absolutely essential. It's a favourite argument thrown up against EmDrive that, it can't work because it doesn't comply with conservation of momentum. Well, that actually is rubbish. It would fly against the physics of Maxwell, Newton, and Einstein. So if you want to argue against those guys, we'll carry on, but good luck with that. No. Why does EmDrive comply with the conservation of momentum? Well, the first thing to understand is that electromagnetic waves carry momentum. They don't carry mass, but they do carry energy, and we're all well aware of the concept of energy and mass having equivalence. Therefore, when an electromagnetic wave is reflected, it produces a force on the reflector, and in free space, this force is given by the equation F equals 2p over c, a very well known, very well accepted equation. What's probably less well understood is that the mechanism that produces this force is exactly the same as that in any electrical machine. Now, in this case, we use the equation F equals BLI, but the two equations can be derived from each other. EmDrive is simply an electrical machine, which does make it perhaps a little bit more familiar to everybody. If you look at the details of this electrical machine, then you have a tapered cavity where the guide velocity, which is the velocity of the electromagnetic wave inside the cavity, the guide velocity is less at the small end than at the large end, giving rise to a force that's less at the small end than it is at the large end. And it's this force difference between the two end plates that produces the thrust. Now, Einstein comes into the argument because special relativity states quite clearly that this guide velocity is independent of the cavity velocity. It's very important, this, because it means that the wave and the cavity itself form an open system, which is why the cavity will indeed accelerate under this force difference that's produced inside it. If the cavity is then free to accelerate, it will have momentum added to it as it accelerates, and the momentum added to the cavity equals the momentum lost by the electromagnetic wave as it bounces up and down the cavity a large number of times and reflects at each end every time. Now, you can verify this by experiment, which has been done many times in many different ways. But you can also verify it with looking at it theoretically in a very simple momentum balance. And we went through this in lecture 1, and the diagram is reproduced in this slide. And if you have any doubts, then sit down, go through this diagram and do the sums yourself. Apply conservation of momentum and you'll see that mt plus me equals 0. That's the conservation of momentum in these terms used in the diagram. You can calculate that mt in this case equals 0.8 m0, where m0 is the momentum in free space. And very important, the direction of mt, and therefore the direction of the acceleration of the cavity, is large end to small end. So, any questions about momentum? First go back, look at this diagram and work it out for yourself. So the second important principle of physics that we need to understand EmDrive is how it complies with the principle of conservation of energy. If we look at the diagram I've shown there, you can see that we have a tapered cavity. Microwave energy is put into the cavity. The energy is lost primarily as thermal energy, but also if the cavity is allowed to accelerate, it is lost by adding to the kinetic energy of the cavity itself. Now, the very important point about this diagram is that within the cavity itself, there is energy stored. So between putting it in and losing it, you actually store part of the energy, and you can calculate the stored energy by multiplying the energy loss per cycle by the Q of the cavity. Very important consideration this is, because the cavity stores the energy, it will have a time constant over which the majority of this energy is stored between input and loss. This short time period is referred to as the cavity time constant. Now, because there is this stored energy, if you hold the cavity stationary, you don't allow it to accelerate, then the input energy will equal the lost thermal energy, because there's no kinetic energy increase because the cavity isn't accelerating. In this particular case, with a fixed cavity, both the Q and the thrust that is produced by the cavity are a maximum. Once you allow the cavity to accelerate, the kinetic energy gained causes the stored energy to decrease. Therefore, the Q and the thrust will decrease. And this is simply EmDrive obeying the conservation of energy. Now, there's also a very interesting aspect to the fact that the cavity stores energy, and that is that when you first switch on the input microwave energy, the stored energy rises as an exponential function. But this rise in stored energy is very quickly overtaken by the rise in kinetic energy, which is a square law. And in this case, if the cavity is completely free to accelerate, both Q and the thrust will fall to 0, which is pretty unsatisfactory if you're switching on the thruster in orbit, or indeed switching it on in a thrust measurement rig that has no load on the cavity itself, no mechanical preload is applied. Once you apply just a very small amount of mechanical preload, then the rise in kinetic energy, which theoretically is at almost infinite rate, if there's no preload, then this rise will very rapidly drop off, and it enables the stored energy rise to maintain above the rise in kinetic energy. So the preload can be applied in orbit by using the AOCS momentum wheel. You can use it by gravity loading, or indeed you can operate a very small solenoid for a tiny amount of time to produce sufficient preload during this rise of stored energy in the cavity itself. Another effect of the conservation of energy is seen in very high Q cavities, which are used in superconducting thrusters. And here what happens is, once you allow the cavity to accelerate, what happens is that you get a Doppler shift in the electromagnetic wave frequency as it bounces backwards and forwards. This Doppler shift also represents an energy loss and is part of the energy balance of an accelerating high Q cavity. Its effect is such that with the extremely high Qs of a superconducting cavity, we need to do something about it, and what is done is to actually pulse modulate the cavity itself, and during the pulse you actually extend the axial length of the cavity to match the decreasing frequency of the travelling wave as it exhibits this Doppler shift. In practice, what is needed is a two-cavity engine, and we switch power input between the two cavities, which enables the power amplifier itself to operate in what's called CW, continuous wave operation, which is the most efficient way of running the system. It also enables the cavity axial extension to be reset during the time that the other cavity is being powered. Once we look at a thruster operating at high velocity, we need to bring the pulse length down to what we term as short pulse modulation, and this is a way of minimizing the Doppler shift loss at high velocity and high values of Q. What this all means is that if you are designing a thruster for a particular vehicle design and a particular mission, you must take account of the acceleration levels and the Qs of the cavity and so on. So in effect, you need to design the way you actually manufacture and operate the thruster according to your mission requirements. And one way to look at this and to actually calibrate each mission, if you like, is to calculate the overall system efficiency for the mission itself. Lecture 3 looked at the equations needed to successfully design an EmDrive cavity, and these equations are well established. They've been used by microwave engineers for many years, so there's nothing new in this cavity design process. The basic thrust equation is shown there, and you can see that T is dependent on power, Q, and something we refer to as the design factor. Now, to maximize the specific thrust in newtons over kilowatts, the Q and the design factor should be maximized. And in a circular cavity, we determine the wavelength of the transmitted wave itself, which is designated lambda g. This is determined essentially by the diameter of the cavity itself. dF is maximized by using the largest practical diameter for the large end and the smallest diameter which is above cutoff for the small end. Now, cutoff is an extremely important consideration, and remarkably, many commercial finite element software packages seem to completely ignore cutoff. This is really quite unfortunate, because many people have used the various commercial packages to design their cavity and wondered why it doesn't work. Well, unfortunately, these packages produce very nice, pretty pictures of the field layouts within the cavity. It makes it much more easy to understand what's happening inside the cavity. But these pictures aren't real. As a very senior government scientist once said, they're Mickey Mouse packages. They give you very pretty pictures, but they do not represent the real world. And in the real world of microwave engineering, cutoff exists, and therefore a good check on your design process, whatever you use, and we'll come to the process that I've used in the next slide, but however you do it, what you should do is to take your small diameter of your cavity below the cutoff diameter and see what your software tells you is going to happen. If it doesn't tell you that the whole thing collapses, then you've got your design process wrong. We actually design the cavity by determining an integer number of half wavelengths, half guide wavelengths, and basically the longer the cavity, the higher the Q, but then you get a larger Doppler shift under acceleration. So as always, design is a compromise. And typically we use a maximum number of half wavelengths. There's 5 for a first generation thruster, and this comes down to 1 for a superconducting cavity. And if you look at the equation for guide wavelength given in the slide, you can see that first of all, it will produce a very non-linear change as the diameter decreases. And indeed, when you reach cutoff, the guide wavelength goes to infinity because the wave stops. And you can see that lambda c is incorporated into the equation. The other thing that happens as the diameter decreases is that the wave impedance changes. The wave impedance is a very important thing to calculate because you have to match the input circuit, the output impedance of your input circuit, with the wave impedance of your cavity. Otherwise, you will never be able to actually get microwave power into the cavity itself. It will simply be dissipated in the input circuit, and this has happened in a number of experimental cavities that I've come across. The equation for wave impedance, which you can see given below, actually means that the wave impedance will go to zero as you get to the cutoff conditions. So again, cutoff, very important in this, in the consideration of where you put the input circuit and indeed how you design the input circuit. The other important point to note about cavity design is that the end plates have to be shaped, and there needs to be close machining tolerances applied to ensure a successful cavity design. As with most engineering design processes, the design of an EmDrive cavity basically requires an iterative numerical approach. I've implemented this concept essentially using standard Excel software. And what you do is you produce a basic spreadsheet begin with, comprising only of 5 columns. And for each row, the columns are calculated for an increment of axial length of 0.1 millimeters. This has proven to be sufficient resolution to get accurate designs. Okay, the column parameters are axial length, internal diameter, guide wavelength, effective wavelength, which is 0.1 divided by the guide wavelength, total effective wavelength, and wave impedance. And essentially, you run the spreadsheet down to the final row, which is where the axial length reaches the length of your cavity design. And at this point, you then vary your initial input frequency, usually not by very much at all, but you vary it until you get an exact total effective wavelength of the required number of half wavelengths to give resonance. A pretty straightforward design process, actually, but once you've done this, it enables you to vary input parameters such as diameters, mode, and axial length, which gives you an engineering feel for the design that you're carrying out. You can envisage the design or the results of the design by plotting, by adding further columns, which enable plots to be made of E field and H field phase responses. You can also add columns to plot the guide wavelength and the wave impedance against axial length, all of which helps to optimize the design. Now, one thing to bear in mind is that the design spreadsheet itself assumes a very simplified geometry of cavity with flat end plates. Now, we've already said that you don't actually get a successful cavity with flat end plates, so you actually have to modify the geometry of the design to incorporate these curved end plates to ensure that you get minimum phase shift across the full wavefront. and this will ensure that you get maximum Q value. Indeed, a calculation of the Q should be done as part of the optimization of the input parameters, and we have carried out quite a large number of cavity designs, and the ones that we've built and tested have shown that a typical accuracy of 0.6% is achieved between design parameters and measured parameters, which is quite acceptable for the first cut of a design. So once you've designed your cavity and manufactured it, the first thing you now need to do is to tune it and electrically test it. As with any high-Q RF device, you do need to tune the cavity principally so you match the input circuit impedance with the wave impedance of the cavity itself. You need a microwave test bench. It must be able to measure frequency, input power, reflected power, and detected power. The heart of this test bench is going to be a stable, accurate, swept frequency source, and all measurements should be done using a two-port technique. And if you actually have a two-port network analyzer available, then this is a very useful piece of equipment to use. Of course, you need to record your test data for later analysis. Now, we've said the cavity needs tuning, and the input circuit itself requires a high-resolution tuning element. And the cavity may need to be tuned by shimming the end plates such that the alignment of these end plates are accurate, and this enables you to achieve a maximum Q value. The typical output of the initial tuning work is shown in the plot of both the detected and reflected power. The detected power is shown in red, the reflected power is shown in blue, and this is actually a plot for the flight thruster. Now, when you carry out the initial small signal tuning, you should aim for a single maximum detected power peak, and at this frequency, the reflected power should give a minimum null at exactly the same frequency as the peak detected power. So you carry out all this tuning at small signal levels, but then of course you should switch to high power inputs, and once you do that, you should also monitor cavity temperature, and you will need to be able to vary the input frequency as the power is increased. And what we did was to develop frequency tracking algorithms to enable us to carry out this frequency tracking, which initially was done automatically, initially done manually. But clearly for flight equipment, you need to utilize automatic frequency tracking using a closed loop control system. Now, at this point, I must mention the fact that before you start to carry out high power testing, you must have prepared written procedures. You must follow these procedures. And before you switch on, you should carry out safety checks on the test equipment itself, which should include ensuring that the grounding of the test equipment is satisfactory, and that you have in place a microwave field strength meter to monitor the levels of leakage from your test equipment, because there will be leakage levels that you must keep well below the safety limits for test personnel. Now, the next thing you'll want to do once you've designed, manufactured and initially tuned and tested your thruster is to measure the thrust that it gives. And even before you design your thrust measurement apparatus, you need to predict what you're going to get, and clearly here you use the thrust equation. Bear in mind that the most variable component of that thrust equation is Q. Therefore, what you should do is to use the measured Q to determine your predicted thrust. Now, whatever balance you use, it should have a resolution of at least 1/10 of the predicted thrust at minimum input power that you're going to apply. And here I must state quite clearly that if you simply place the thruster on a balance, electronic balance for instance, switch it on, you will not measure thrust. Conservation of momentum, Newton's laws show quite clearly that this will not happen. So don't even bother to try. Unless, of course, you simply want to prove that EmDrive complies with the conservation of momentum and also with Newton's laws. What you need to do is to build a more complex balance. We have used what we call a composite balance, using a suspension spring together with an electronic balance. We've used a beam balance, pendulum type balances, and a rotary test rig on an air bearing. Whatever test rig you build, you need to ensure that there is a very small preload applied, and this is particularly necessary when you use a pendulum type test rig, because by definition at the 0 point of a pendulum there will be no preload. Now, the input power needs to be coupled to the input circuit of the cavity, and you need to do this without any mechanical linkage, otherwise you'll get very significant spurious forces. We've shown how we do this, and the thing to bear in mind, however, is that once you have no mechanical linkage to the cavity, you must nevertheless ensure that it is grounded. Otherwise you'll have a very dangerous situation with the cavity itself floating up to the voltage levels of your input power amplifier, and if it's a magnetron or or indeed a travelling wave tube amplifier, these can be very high voltages and you will end up with a dangerous piece of test equipment. You can actually measure both thrust and reaction force if you carefully set up a beam balance, and we've actually done this. And if you vary the preload down to a point when you can actually lift off the cavity from the balance rig itself, this shows full compliance with theory, which is actually very satisfying to see. If you do temperature measurements during high power testing and high power thrust measurements, if you take the temperatures of both end plates, put them through some maths, you can get a very satisfying thermal validation of the design factor and therefore the basic theory behind EmDrive. And finally, if you do measure the acceleration of a moving thruster, either rotating or in a vertical thrust measurement arrangement, you can verify the static thrust that you will have measured by simple application of Newton's laws, which is a very satisfying thing to do. Lecture 7 covered the various technology development stages, which we split into 4 generations of technology. Now, the first and second generation work was fairly extensively published and included a lot of experimental results, both positive and negative. However, once we moved into the third generation and fourth generation work, publication was severely restricted, shall we say, and there were very good reasons for this, which we will briefly cover at the end of this particular lecture. So our first generation technology, ambient temperature cavities, we use them in experimental and flight thrusters. There's still wide applications for first generation, including primary propulsion and attitude and orbit control systems for satellite types, from the large geostationary communication satellites down to the CubeSats. And you can see a diagram of a first generation CubeSat given in the slide. Further missions included science probes and space tugs, which we've also covered in later lectures. The second generation was where we moved to superconducting cavities, initially cooled with liquid nitrogen and then liquid hydrogen, and where we were attempting to overcome the small values of specific thrust by essentially ramping up the Q many orders of magnitude. However, in doing this, we came across the Doppler shift problem, which severely limited the acceleration you could use. Nevertheless, there are applications, and we proposed a demonstrator UAV, which you can see illustrated in the slide. This could well be used as a step in the development program that we'll talk about later in this lecture. One other area of applications for second generation is for marine use, where almost by definition, certainly for very large marine vessels, accelerations are extremely low. Now, we went on to third generation technology, basically to compensate for the Doppler shift. We ended up using multiple cavities, pulse operation, and axial length and frequency control, basically to overcome the Doppler shift. It couldn't be completely overcome, but nevertheless, we were able to improve performances significantly. However, as we'll mention, applications for third generation technology really were superseded by the fourth generation technology, where we looked at short pulse modulation applied to the third generation builds, because we needed to improve the performance, particularly the acceleration, to the sort of levels that seem to have been demonstrated from the flight videos of the so-called UAPs, or unexplained aerial phenomena, that were released around 2017, something like that. The short pulse modulation is where the pulse length is actually less than the cavity time constant. We've discussed some of the implications of this, but the advantages is that you get thrust, much higher levels of thrust at acceleration levels that were not achievable with third generation. However, to maintain the thrust, acceleration and system efficiencies, the pulse length itself has to decrease as the velocity increases. Okay, so the applications here are many and varied. They include the infamous UAPs, but cover deep space probes, personal air vehicles, space planes and heavy launch vehicles. And you can see an illustration of a fourth generation personal space plane in the slide. So this lecture covered the missional analysis method, basically for vehicles using a 950 megahertz fourth generation engine. And there's a whole family of these vehicles. The first vehicle we used to describe the analysis technique is the deep space probe. And the analysis techniques uses essentially the good old Excel spreadsheet again. Now, the inputs to the spreadsheet are time increment and vehicle acceleration for the first two columns, and then basically using the specific thrust of the vehicle, the total and the total thrust and the mission and the vehicle mass, you then calculate the mission parameters for increasing flight time. Now, the equations you use are very standard equations of mechanics. There's nothing magic about them, and they give you the ability to really vary mission parameters at will, and whilst ensuring that the end results are going to be correct. You need to calculate the liquid hydrogen usage because the fuel mass will obviously go down as the mission flight time increases, and you calculate the liquid hydrogen usage from the latent heat of evaporation of liquid hydrogen because it's boiled off to maintain the 20 degrees K temperature. Now, some of the cold gas is used in the fuel cells to produce the electrical power, but a large amount is simply vented off. You need to calculate the liquid oxygen usage for the fuel cells, and this is clearly going to be based on the DC power requirements into the SSPA itself. So you need to know the efficiency of the power amplifier. We gave the mission analysis results for an in-space launch of a deep space probe. This was the first simple mission we looked at. And then described a heavy launch vehicle, and we showed the additional spreadsheet columns that are needed to incorporate the ground launch mission. We gave the results then for a heavy launch vehicle to geostationary orbit with a 65-ton payload, and this has been our goal all the way through the EmDrive program to be able to carry out this mission and to give the very low launch costs that are going to be necessary to ensure there is a good commercial argument for developing EmDrive thrusters. We illustrated a personal space plane configured for a 6-person mission to the moon, and the mission analysis results are given for the flight to the moon, a vertical landing and a return. And one of the important outputs from the mission analysis needs to be the fuel margin you've got at the end of the mission for safety reasons. What we then suggested were a number of trainee exercises for a whole family of vehicles, which included suborbital passenger and cargo missions, and would help to illustrate the financial viability of any development program. This lecture expanded the scope of applications, and the first one we described was a two-person air taxi using what was essentially a very simple personal air vehicle using 4 fixed 1.5 gigahertz third generation engines. We then moved on to fourth generation engines using a deep space probe, where you could fly science missions out to all the planets of the solar system. And we mentioned the very high volume application that could be occurred during prospecting asteroids for high value platinum group metals. An interesting application of the deep space probe was to use the high kinetic energy that you can generate in a deep space probe and use it in asteroid deflection missions. We looked at the original application for heavy launch vehicles and how they could be used to launch components of a solar power satellite to geostationary orbit. We came up with an estimated launch cost of $8.4 per kilogram, which can be compared to current best costs of about $1,000 per kilogram using conventional launch systems. So there's a huge saving potential there. In addition, if we're looking at solar power satellites, you can get a good mass reduction by essentially building the satellites using flexible arrays, which are held in tension by first generation space tugs. This reduces the estimated mass of a rigid 2 gigawatt satellite from currently estimated around 10,000 tons down to 2,606 tons. And the space tug is then available, or the space tugs are then available to provide satellite pointing and also compensation for the sun's radiation pressure on what turns out to be a 3.6 kilometer diameter array. So this is all pretty big stuff. You can use similar construction techniques for orbital sunshades in 12-hour orbits. And we've also looked at further applications of the heavy launch vehicle for point-to-point cargo missions on Earth, support of manned missions to Mars, and in the mining of asteroids. We also looked at a personal Mars spaceplane with a crew of 3 and saw how it would be used to put together the first manned base on Mars. And we looked at the sequence of 9 HLV missions and 2 PSP missions to make this possible. A further development of the PSP is described, which was a very interesting multi-domain vehicle for 8 people. This would operate in space, air, or indeed on the water. And we also looked at a single pilot freight version of this. And finally, we just had to do an all-domain unmanned vehicle proposed for observation missions in space, air, or underwater. And what this really clearly showed that if you want to explain the performance of these UAPs, you do not need to bring in extraterrestrial technology. EmDrive will do it all for you. This slide shows a table of missions for both first generation and fourth generation technology. And the important thing about the table is that you need to look at the comparison columns where we compare what an EmDrive vehicle would do compared to a conventionally propelled vehicle, if indeed one was available. And you can see that over the 16 missions that have been shown in this table, each time the comparison shows that EmDrive has a substantial advantage over conventional propulsion. I won't attempt to go through the full table because there's a lot there, so I'll leave you to look at it in your own time. And if you want to look at the details of each of these missions, I've also given the references, which are the page numbers in the book entitled EmDrive Advances in Spacecraft Thrusters and Propulsion Systems. So at the very beginning of these lectures, I said that EmDrive Basics is a course which is the first part of a training program. And here we see an outline of what that training program would be. And the idea is that it will consolidate the knowledge learnt in over the last 10 lectures. And it will consolidate the knowledge by basically getting a team of engineers to design, manufacture, build and test a first generation EmDrive thruster. This is all learning by doing, which is by far the best way of learning. The idea is you will end up at the end of this 12-week course with a proof of concept thruster, which hopefully will enable you to encourage investment into the subsequent development programs. The course training program should also include the specification and mission planning for a number of EmDrive vehicles. This again is an attempt to provide the reasoning behind why significant investment should be made in a subsequent development program. The course we suggest would last 12 weeks. It covers basically this set of lectures: thruster design and manufacture, test rig design and manufacture, low power tuning, high power testing, and then vehicle specification and mission planning. I would recommend a minimum of 3 trainees, and I would suggest that one of them should be a pretty experienced microwave engineer who can actually make sure that the experimental work is done correctly and safely, with much emphasis on the safety aspects of it. Total test equipment and hardware costs I've estimated for this particular training program at £100,000 UK. So now we'll look at what could happen following the training program and how we would plan to design, build and test, first of all, a UAV demonstrator. This is the simple one that we've talked about before, and I envisage an 18-month program at a cost of about £20 million to provide a first flight demonstration of this vehicle. For the last 6 months of this program, I would suggest we would start a 4th generation head start program, essentially to lay down the specification and do the program and financial planning for what follows, which would be a parallel development program of the multi-domain vehicle and the personal air vehicle. Now, the idea is that we would complete the development of the personal air vehicle at the 4.5-year point, and the subsequent commercialization of this vehicle would then provide a revenue stream to complete the multi-domain vehicle development, and most importantly to go into the qualification program, the space qualification program of this vehicle. Now, any space qualification program is inevitably expensive and quite rigorous. Um, but nevertheless, we can start the beginnings of the fleet manufacture program at the beginning of the qualification period, because you have fixed the design at that stage. The end product is that we should be able to start initial space tourism operations by the 7th year, and there we would estimate a need for a fleet of 4 multi-domain vehicles, each with a target cost of £200 million each. So now we'll look at the implications of EmDrive in this last slide. And you can see from the little block diagram that I've given at the top that I consider that all innovation actually is driven by a combination of 3 forces: fear, greed, or curiosity. And EmDrive is really no exception. The initial suggestions for EmDrive came from the defence establishment. I confess a lot of the subsequent work that I've done particularly has been out of pure curiosity, but other people have chipped in out of greed, or at least a sense of investing sensibly in a research project. We have to look at the problems that EmDrive can address to look at the value of it. And I suggested 4 problems: security, energy, transport, and climate. And you can see these are major problems that the world faces, particularly in terms of climate change. So we have the potential here for enabling solutions to these basically existential problems for the world. Now, the solutions that EmDrive offers include asteroid deflection, which indeed may actually save the world from being destroyed, or at least humanity from being destroyed. Solar power satellites, which have always been a major application with significant improvements for power generation, global power generation. A whole host of vehicles will help solve transportation problems, and we have orbiting sunshades to help the climate change, even though the solar power satellites will start to lower the climate change problem straight away. And what I'm suggesting, or what I have suggested in the last couple of slides, is that these solutions can all become available within about 10 years. So people are beginning, they should, and they are actually beginning to take notice of EmDrive and what it can do. And this is good, but it does introduce risks themselves. And we have to acknowledge that EmDrive is above all a very disruptive technology, and which will cause people to be very cautious and in some cases try and suppress the development programs. So the risks are, as with any engineering development program, technical risks. But let's face it, they're fun to solve. So, and they are all soluble. We can see that there is no insoluble problems here. The financial risks are different in that at first sight it might appear quite risky. We're asking to invest significant money in covering the early development costs. But then when you look at the potential return for indeed any of the proposed commercial applications, suddenly you have a huge potential return. There's nothing that can touch EmDrive as far as solving the sort of problems that we've talked about. Finally, we have to look at what I call the political costs. And the political risks, sorry. I've actually been subject to some of the political costs already, so I know quite a bit about them. First of all, you've got academic inertia. Well, this is sort of normal, you know. We always used to say that academia is 10 years behind industry, and it's no exception as far as EmDrive is concerned. But the problem is that in industry, you have some very large vested interests. Look at the problems that we're going to solve: security, energy, transport, and climate. These all involve huge industrial organizations. And the last thing they want to do is to have their current technologies completely overturned by EmDrive, which is what is going to happen. EmDrive will unfortunately make obsolete a lot of the technology that the present world is built upon. So this is going to cause a lot of attempts to suppress the technology. And finally, of course, we have national security concerns, ones which I'm very aware of and have great sympathy for, because if you look at the sort of vehicles that we've proposed for the various commercial applications and just think about how the defence industry would use them, you can see that suddenly a lot of weapons platforms and indeed weapons themselves are going to become obsolete. And so whoever really controls EmDrive exercises pretty enormous commercial and political power, which will make itself felt over the development programs, I'm sure. But throughout the work that I hope that you guys are going to start on next, you need to remember that a successful development of EmDrive can actually save the world. And I leave you with that thought. Thank you.